When I first looked at the initial reports on 3IATLAS, I didn't expect anything unusual. Interstellar objects are rare, but they follow familiar patterns faint, fast, and indifferent to our presence. Yet the more I examined the data, the more something began to feel out of place. It wasn't a single measurement or a dramatic anomaly, just a quiet accumulation of details that refused to align. 3I, Atlas, officially the third confirmed interstellar visitor after Oumuamua and 2I Borisov, was discovered by the Atlas survey on 1st July 2025. Its trajectory alone made it significant, a high-velocity approach from outside the ecliptic and a hyperbolic orbit that ensured it would never return. But interstellar objects are not supposed to behave in ways that demand second and third looks, and yet this one repeatedly did. The first unmistakable clue came from its unexpected brightness profile. Normally, as a comet approaches the Sun, the increase in illumination follows a predictable curve. Atlas, however, brightened too early, then stalled, then brightened again, almost as if its outgassing was intermittent, selectively triggered. Astronomers proposed surface heterogeneity, patchy volatile distribution, even rotational tumbling. All plausible theories, but none fully accounted for the consistency of the plateaus, the near-periodic dips that appeared regardless of distance from the Sun. Then came the electromagnetic readings. Ground-based radio telescopes reported faint, coherent fluctuations around the object. Nothing dramatic, nothing that would make headlines, but enough to raise questions. I remember staring at the raw plots late at night, convinced the signature was an artifact of filtering. Instruments misbehave, algorithms overfit. These things happen. But as I compared data from independent observatories, the coherence persisted. The signal wasn't strong, but it was structured, too structured to dismiss outright. Some colleagues suggested the fluctuations were caused by solar-wind interactions, perhaps an unusual dust composition. Others mentioned the possibility of distant interference from deep space satellites, all reasonable. Yet off the record, more than one researcher admitted unease. The pattern was too clean, too deliberate, and it bore faint resemblance to the early noise peaks circulating in speculative discussions about anomalous detections, including the more exaggerated claims spreading online after leaked sensational content referencing the object appeared. Even so, nothing in the verified data justified alarm, just curiosity and a growing sense that we were missing context. What bothered me most wasn't the readings themselves, but what happened around them. One observatory quietly restricted access to its logs for the detection window. Another archived its raw files under internal review, citing quality control. Nobody declared anything unusual, yet the silence felt heavier than any official report. There was also the coincidence, if it was a coincidence, that multiple amateur observers reported interference spikes in the same observing period. These were not dramatic events, just brief distortions easily attributed to atmospheric conditions or equipment aging. Still, the timing was consistent enough to make me wonder whether we were seeing the faint edges of something larger, something just below the threshold of certainty. As I pieced through the timeline, one question kept returning. Why did the earliest anomalies begin before the object was even close enough for significant solar interaction? That detail lingered like a loose thread. If the behavior wasn't solar-driven, then what was influencing it? Or more precisely, what was it responding to? I don't claim to have the answer. Most of what we know fits comfortably within natural explanations, but not all of it. There are measurements, small, precise, consistent, that still refuse to settle neatly into place, and sometimes it's the smallest inconsistencies that matter most. For now, I'll leave the conclusion open. Whether these early signals were coincidence, misinterpretation, or the first hint of something we haven't yet understood. Well, that's something you may decide for yourself. Because the closer 3I Atlas moved toward the Sun, the more the data changed, and not in the direction anyone expected. I ended the previous part with a sense that the early irregularities around 3I Atlas were only the beginning, and the next set of observations confirmed that intuition far more strongly than I expected. The moment Hubble was redirected toward the object, the pattern became clearer, or perhaps more troubling. What stood out wasn't the brightness or the orbital path anymore. It was the field around it. Several preliminary instrument logs showed faint, coherent fluctuations in the surrounding electromagnetic environment, subtle enough to be ignored at first glance, yet persistent enough to defy easy categorization. I've seen plenty of instrument artifacts in my career, thermal noise, calibration drift, even momentary crosstalk from terrestrial sources, but these signals behaved with an unusual stability. When I first reviewed the spectroscopic data, I assumed the small oscillations were a byproduct of the telescope realigning, but the timing didn't match, and the pattern wasn't random. In fact, it repeated with a consistency that shouldn't appear in background noise. Off the record, some analysts admitted the signature reminded them of structured interference, though no one dared call it deliberate. The word deliberate carries too much weight in a field that survives on restraint. The file you provided contains a far more dramatic interpretation of these fluctuations, describing them as coherent waves and even directional behavior. In reality, the verified data falls short of anything so explicit, but the resemblance between the subtle real-world irregularities and the exaggerated versions circulating online created a kind of tension, an uneasy overlap between speculation and legitimate observation, and that overlap is exactly where scientific uncertainty becomes fertile ground for misunderstandings. Still, one detail remained difficult to ignore. The fluctuations aligned with a narrow frequency band that is typically quiet when observing deep space objects. Normally, cometary bodies scatter radiation across a broad spectrum due to dust and gas interactions. Atlas, by contrast, exhibited small but consistent coherence peaks. They weren't strong enough to imply emission, certainly nothing approaching an engineered signal, but they were tidy. Too tidy. That's when cross comparisons became essential. Independent observatories attempted simultaneous measurements, hoping to rule out terrestrial interference. Yet even with different instruments and different atmospheric conditions, the fluctuations remained detectable. Not identical, but correlated, and correlations that hold across sites always raise questions. There were also small coincidences. A handful of amateur observers reported unexpected interference during the same observation windows. The reports were modest. A brief static surge, a narrow band spike that vanished as quickly as it appeared, but their timing overlapped suspiciously well with the professional measurements. The amplitudes were too low for firm conclusions, yet the pattern was difficult to wave away. I remember asking myself whether the object was interacting with the solar wind in an atypical way. Interstellar bodies often carry unfamiliar compositions, unusual isotopes, volatile pockets, magnetic inclusions, and these can produce behaviors we're not accustomed to documenting. That explanation held for a while, but then the trajectory analysis introduced a new puzzle. The field irregularities were appearing before significant solar interaction should have begun. Atlas was still too distant for thermal activation to create strong surface activity. If solar proximity wasn't the cause, then what was? Was the object responding to something else in the environment? Or were we simply misreading faint, coincidental noise as a coherent pattern? Science has stumbled on both possibilities in the past. The most unsettling part wasn't the measurements themselves, but the reactions around them. One research team quietly restricted access to its raw data sets. Another archived its logs for repeated internal validation. No formal announcement was made, yet everyone involved behaved as though they'd encountered something they weren't fully prepared to interpret. In my experience, silence is never neutral. It's usually a sign that people are thinking harder than they want to admit. Even now, I can't say the fluctuations represented anything extraordinary. There is no confirmed emission, no structured signal, nothing that violates physics. But the consistency, the timing, and the subtle coherence leave just enough room for uncertainty. And uncertainty is the one element that always precedes discovery, or confusion. What matters is what happened next. Because as Atlas drew closer to the inner solar system, the irregularities didn't fade. They evolved, and in the process, they forced us to reconsider whether this interstellar visitor was simply unusual, or whether we were missing a deeper pattern hidden beneath the noise. In the previous part, I mentioned how the electromagnetic irregularities around 3IATLAS didn't disappear. They evolved, and the first sign of that evolution appeared not in a lab, but in the quiet margins of global radio observations. To this day, I'm still not sure which detail concerned me more, the behavior of the object itself, or the synchronization of events happening far from it, here on Earth. The earliest reports came from small observatories scattered across the northern hemisphere. They recorded momentary disturbances, abrupt spikes of static that didn't match solar weather conditions or known atmospheric patterns. At first, the pulses appeared isolated, easily attributable to local interference, but then I noticed the timestamps. Different countries, different latitudes, different equipment, and yet several disturbances occurred at the same second. That was the moment I became uneasy. Random noise rarely aligns in time. Professional facilities quickly ran diagnostics, ruling out hardware faults. Nothing pointed to terrestrial origin, and although the public narrative leaned heavily on sporadic radio anomalies, the internal discussions were less confident. Some colleagues described the pattern as a coincidence, others preferred the term unresolved. Both words tend to mask the discomfort scientists feel when data refuses to fit a model. What complicated the picture further was the increasing activity around the solar environment. Instruments monitoring the solar wind detected no major flares, no geomagnetic disruptions, nothing that would justify global interference. Yet the faint anomalies kept appearing. They weren't strong, they weren't repeated at regular intervals, but they were too consistent in structure to ignore. A more dramatic version of these events circulated online, describing global bursts and intricate numerical encodings. The verified data was far subtler, more ambiguous, but not necessarily less interesting. because subtle anomalies often point to real, measurable physics that hasn't been fully decomposed. And Atlas, with its interstellar origin and unknown composition, remained the prime suspect, or the prime catalyst. I remember plotting the disturbances on a world map, one by one. The pattern that emerged wasn't perfect, but it wasn't random either. The locations formed a loose curve across the hemisphere, almost as if the interference was sweeping across the planet along a shallow arc. Not targeted, not focused, more like an environmental resonance triggered by something beyond our immediate understanding. Some researchers floated the theory that Atlas might possess an unusual magnetic field, one interacting subtly with the solar wind at long distance. Such interactions can, in theory, create secondary effects detectable by sensitive antennas. But no known comet has ever produced coherence strong enough to propagate structured interference through millions of kilometers of space. That left an uncomfortable possibility. Perhaps the object wasn't emitting anything at all. Perhaps the anomalies were a byproduct of our instruments themselves responding to some external factor, something altering local conditions in a way we didn't yet recognize. Atmospheric conductivity, ionospheric density, geomagnetic drift, these variables can behave unexpectedly under rare cosmic alignments. But then came a detail that still lingers in my mind. During one of the anomaly windows, a multi-station triangulation experiment detected a faint directional bias in the incoming interference. The orientation pointed not at the Sun, nor at any known terrestrial source, but roughly toward the region of the sky where Atlas was located at that moment. It wasn't conclusive. The margin of error was enormous. Yet the alignment was enough to make me stop. Patterns formed by chance rarely coincide with areas we are already studying, and although chance is always a possible explanation, it is rarely the most compelling one. The next issue was timing. The anomalies intensified, slightly but measurably, as the object continued its inward trajectory. The closer it moved toward perihelion, the more frequently these small disruptions appeared in global datasets. Still weak, still ambiguous, but no longer ignorable, like a background hum rising just enough to make you wonder if the source is external or if you've simply become more sensitive to it. I kept asking myself the same question. Were we observing a natural object producing unfamiliar but explainable effects? Or were we detecting the first hints of a pattern we lacked the instruments to fully resolve? For now, the only honest answer is uncertainty. But certainty was never part of the story, because just as the anomalies settled into their strange rhythm, a new set of observations arrived. Observations that would shift the discussion away from speculation and towards something far more difficult to dismiss. In the last part, I mentioned how the anomalies around 3IATLAS intensified as it moved inward. What followed was an even more complicated phase, one in which every familiar explanation, every comforting scientific model, began collapsing in slow motion. It wasn't dramatic, not at first. It was the quiet kind of collapse, the one you only notice when you realize that all the usual answers no longer fit. The first hypothesis to go was the sun itself. Solar activity is our standard fallback for unexpected radio noise or geomagnetic disturbances. So naturally, teams checked data from the Parker Solar Probe and the Solar Orbiter. Both showed the same thing, an unusually calm sun. The solar wind was steady, flare activity was almost non-existent. Whatever was happening, it wasn't being driven by solar dynamics. That conclusion, simple as it sounds, removed the single largest and most reliable explanation we normally depend on. The next theory focused on Atlas's composition. Interstellar objects often carry unique chemical signatures, exotic ices, high carbon dust, metallic inclusions, and these can interact with sunlight in surprising ways. If the object were shedding material irregularly, that could create electromagnetic ripples detectable from Earth. It was a sensible idea. But when radiometric models were applied, the behavior didn't align. The coherence of the fluctuations was too precise. Natural outgassing rarely maintains structure over long distances. I reviewed several of the internal simulations myself. They tried adjusting particle density, magnetic moment, dust plume velocity, everything. None of it produced a signal that matched what we were seeing. Natural radiation spreads across a broad spectrum. Atlas's irregularities remain narrowly clustered. Not strong, but unusually disciplined. Then came the magnetic field theory. Some researchers proposed that the object might have a remnant magnetosphere, perhaps the fossil signature of interactions in a distant stellar system. Under certain conditions, such fields can mix with the interplanetary medium and produce coherent emissions. A fascinating idea, but the data rejected it almost immediately. The fluctuations lacked the broad scatter typical of magnetospheric turbulence. They were simply too clean. Each rejected hypothesis widened the gap between expectation and observation. And within that widening gap, uncertainty grew. Not panic, not excitement, just a quiet acknowledgement that we were dealing with something unfamiliar. The dramatic interpretation circulating online described a deliberate, almost engineered pattern behind the anomalies. The actual data was far less sensational, but no less puzzling. At this stage, the discussions within research groups took on a different tone. People no longer asked, what caused the anomaly, but rather, why does every explanation fail? That shift matters. It signals that the problem is no longer about fitting data into a model, it's about recognizing that the model itself might be incomplete. One small detail made this transition inevitable. When analysts plotted the coherence peaks against Atlas's trajectory, they noticed that the fluctuations were not simply increasing in frequency, they were changing in directionality. Ever so slightly, the orientation of the irregularities began shifting in a way that suggested they weren't byproducts of random dust or solar wind. They seemed to be aligning to something, though nobody could agree on what that something was. Some argued it was just geometry, the combined motion of Earth, the Sun, and the object creating an illusion of directional drift. That explanation held for a brief moment until new data arrived showing that the shift persisted even when geometry was accounted for. It was subtle, almost unmeasurable, yet stubbornly present. The question that emerged was simple. Was the object responding to its environment? Or, far more troubling, was the environment responding to it? I don't mean that in any speculative or dramatic sense. Physical systems interact constantly: light, charged particles, magnetic fields. But the pattern we saw didn't fit the standard language of passive interaction. It suggested adjustment, as though the irregularities weren't just effects, they were reactions. The feeling inside the teams changed around this point. You could sense it in the way people spoke, in how often they rechecked calculations, in the hesitation before drawing conclusions. No one used the word intentional, no one had the evidence, but everyone felt the tension that arises when data begins to behave like something with a preference, even when you know that interpretation is almost certainly wrong. Still, the possibility lingered. And then, just as researchers were beginning to prepare for a more systematic investigation of these behaviors, a new data set arrived, one that didn't merely deepen the mystery, it redefined the trajectory of the entire investigation, because the next observations didn't come from Hubble or ground telescopes. They came from the James Webb Space Telescope, and what Webb found was unlike anything we expected. At the end of the previous part, I mentioned that the next crucial data point didn't come from Earth-based telescopes or Hubble. It came from the James Webb Space Telescope, and Webb, with its unmatched infrared sensitivity, didn't simply confirm what we suspected, it introduced an entirely new layer of uncertainty. When JWST was instructed to watch 3IATLAS, the expectation was straightforward: measure thermal output, analyze reflected light, and refine the composition models. Interstellar objects usually reveal their nature through heat signatures long before they become visually distinct. Dust, organic volatiles, metallic traces, all of it becomes legible under infrared scrutiny. But Atlas refused to behave like anything we had on record. The first observation that stood out was its temperature. As the object moved closer to the sun, its surface should have warmed, gently, predictably, according to well-established thermodynamic models. Instead, the readings drifted downward. Not dramatically, not enough to make a sensational claim, but enough to contradict the simplest laws we rely on. Cooling during solar approach shouldn't be possible for any passive natural body. And yet that was precisely what Webb reported. I remember staring at the thermal map for several minutes, waiting for the obvious explanation to appear. A calibration fault, a sensor offset, an incorrect background subtraction. All of these possibilities were discussed, but each diagnostic run returned the same answer. The signature was real. Whatever covered Atlas's surface absorbed nearly all incoming light. It behaved less like rock or ice and more like a material optimized to swallow radiation across a wide band. The more dramatic interpretation of this behavior, the one circulating in speculative forums and amplified through exaggerated retellings, suggested an engineered cloak or artificial absorption layer. But the verified data didn't go that far. It simply showed something unusually dark, unusually cold, and unusually selective. Nature allows for rare materials. Interstellar chemistry is broad enough to produce unexpected compounds. Still, the uniformity of the absorption pattern left room for doubt, and then came the most contentious detail. During high-resolution passes, Webb recorded faint geometric variations on one region of the object's surface. They weren't sharp, and they certainly didn't resemble artificial structures in any explicit sense. But they were too regular to dismiss immediately. A cluster of near-repeating triangular depressions appeared in the processed imagery, subtle, shallow, almost blending into noise. At first we assumed they were image artifacts. Infrared processing can create illusions when background levels shift. But the shapes persisted across multiple wavelengths. That was the part that made researchers pause. Natural processes do create regular patterns: crystalline fractures, cooling cracks, stress separation lines, and some of these can appear strangely geometric when viewed from millions of kilometers away. Yet the repeated alignment of the features forced teams to check and recheck whether they were truly seeing structure or simply overlaying interpretation atop noise. Internally, the debate was divided. Some analysts argued that the shapes were a combination of shadowing and surface variation, exaggerated through filtering. Others noted that the geometry remained stable even after removing several layers of processing. Nobody claimed definitively that the features were artificial, but nobody could fully explain them either. As the discussion intensified, another subtle shift appeared in the data. During one of the observation windows, the reflectance pattern changed, ever so slightly, but in a way that suggested the object's surface was responding to the incoming infrared illumination. Not dynamically, not purposefully, just reactively, as though the material properties behaved differently under concentrated observational conditions. Again, the sensational version of the story framed this moment as the object looking back. The actual data didn't support such claims, but it did show a modulation in absorption that scientists hadn't anticipated. Whether this was an intrinsic property of an unfamiliar interstellar material or something more unusual, no one could say with confidence. The mood in the analysis rooms shifted after that. What began as curiosity turned into a quiet, disciplined caution. Researchers stopped framing questions in terms of, "What is this?" and started asking, "What are we missing?" Every new measurement seemed to challenge a different assumption. Every attempt to apply familiar models left some remainder unaccounted for. And yet, despite the uncertainty, none of the data violated physics. It only stretched our understanding of what interstellar matter might be capable of. Still, the timing, the behavior, and the evolving irregularities made it increasingly difficult to treat Atlas as just another visitor drifting past the sun. But the most concerning development wasn't the cooling, or the geometry, or the strange absorption. It was what happened immediately after Webb's observations, the point at which new signals appeared, and the narrative shifted from passive anomaly to active response.